Web scraping with Julia. So I want to show you sort of the elements that go into creating a web scraper. And I think in Julia now we have all the elements built in. And today I want to show you how we can use those elements to sort of scrape the web on your own. So let's start by looking at, Let's start by looking at Stack Overflow, which is always useful as, where did my browser go? Sorry about that. Yeah, there. So let's start by looking at Stack Overflow, which generally has a pretty open scraping policy, so that's safe to use. This is the homepage of Stack Overflow. We want to look at all the JuliaLang posts. So I click on the JuliaLang tag, and then I go down, and I want 50 per page, which is great. So let's see what the URL is. That's the URL that we want to start scraping. So let's copy that and go on, right? So the first thing that you need is install a few packages, and I'll talk about what these packages do in a minute. So you install a package called Cascadia and the HTTP package to actually do the HTML HTTP request, and then you load them up. Hopefully that's visible. Maybe I'll increase the size a little bit. Right, and then we say http.get with that URL that we just got from Stack Overflow, right? And that returns an HTTP response object that includes some headers and the body of the response, right? Which in this case is an HTML body, right? So the type of that response is http.response, which is part of the package. And then we convert it into a string because the response object is a complicated object with many different parts. We just want a string representation of the body, and you do that using the take function. And again, this is part of the http.jl package. Right. The thing that you want to do next is to parse this HTML into a data structure that you can manipulate. The HTML itself comes to you first as just a plain string, but it has that structure that you want to query, that you want to process. So we use this function called parse HTML, which is part of a package called Gumbo. It's a C library written by some people at Google, and it's been wrapped in Julia by Porter James. And it's a great little package that does a little thing very well. So we parse the string using the parse HTML function, and that returns us an HTML document object, which is really the root of a tree. HTML object is represented typically as a tree, and that's what this representation is. So right, so this h, the local variable h, is an HTML document, which is the tree. Right. So the type of h is gumbo.html document. So as I said, this is a tree. So as a tree, you can traverse it like a tree. So you can say the root element, the first child of the root element, and then the first child of that child element. And that turns out to be this title tag, right? It says title, that's the title of the page, right? So you can traverse this HTML document as a tree. And there are, in Gumbo, methods for post-order DFS search and pre-order DFS search and all those tree or graph methods. But when you want to extract data out of a page, you don't want to actually have to write code to traverse it every time, right? So what you want is really a query language, right? So the query language that you want, there are various kinds of query language that you could use. One of the standard ones is XPath, which is a query language for XML documents. But HTML is really awkward to work as an XML, right? It sometimes works, but many times HTML is not well formed, and XPath is a very verbose language. So the language that you typically use when you're scraping the web is the CSS query language. So this is the language that you use when you write CSS, right? So CSS is the way you style a page, and when you're styling a page, you need to say, this is the style that you apply to this element. And the way you specify this element that you want to apply styles to is this CSS language, right? So you reference elements in the page by their ID, or by their styles, or by their position in the tree, right? So let's go back and take a quick look at this page, the Stack Overflow page. You can see these elements here, which are the questions, right? And that's what we want to extract. So you would typically go and inspect the HTML in your browser, and you see, if you look at the bottom of the screen here and the highlight that happens when I move my cursor, you can see what those elements are. And so it seems that all the questions are in these divs that are tagged as class equals question summary, right? So each of these is a question summary, and that is really what we want to extract when we want to see what are the elements on the page. So the Cascadia package, which is we installed earlier, has this ability to query HTML using CSS selectors. So we create a selector called question summary, and then just like a regular expression, you can match all. So we match the selector against our tree, which is the HTML tree, and we get the match. And it says 50 element HTML nodes, and each of those elements is the div that I extracted, right? So I can do things like that. Now after I match all, I can also match user details, which gives me the author. So if I go back to this HTML element here, the question summary, you go down, and there will be somewhere author element, right? Which will tell you who the author of that page is. So that's the user info, and that's the author, right? So you can get the user detail, that'll give you the author, and you can then say the child of the author element is the actual HTML text, and the text method will actually return the string that defines it, right? So this is how you can extract elements from the page. So we can go down and okay, sorry, I did that again. We can go back to the Stack Overflow page. At the bottom, you will see there is something that says next page, right? So over here, there's the button that says next page. We inspect that, and it says that's a span with a class called next. So let's go back and extract that. So I say cell, which is another way of creating a selector like a regular expression. You can say cell quotes with this element which says this has a attribute rel equals next, right? And that's what the HTML has. And I select for that, and that gives me this href, which is the link to the next page. That link has, from this element, I can extract the link. So I get the first element, and then I get the attribute called href. That returns the link. And then that's a relative link, so I add a base URL, and I get the new link, right, which I have just extracted from the previous page. And that returns me this response. I can then, just to show you that if you match something that doesn't exist, it returns a 0 element array. So I can then put this together in a loop that says, for every page, get the next link, count the number of questions in there, and then traverse the next link, right? And keep adding the number of questions that you get. And that, if you run this code, you will see that there are a total of 3,056 questions on Julia on Stack Overflow, right? It takes about 28 seconds. This was run yesterday night, so I think today there are a couple more if you are looking right now. Right. So let's generalize a little bit. So the previous function had the tag hard-coded. I have exactly the same function, but the tag is now a parameter, the parameter tag at the top of the function definition. And if you see in the URL, I reference that. So this function, exactly the same, will return the number of questions for different tags. I can then run this in parallel. So while Julia is single-threaded and runs in a single process by default, I/O is asynchronous, right? And when you're web scraping, most of your time is spent on I/O. So you can so even without doing distributed computing, you can just wrap this in a sync async block. So what the sync async block does is it'll run the count queue function asynchronously, and then it'll wait for all the async tasks to be done, and that waiting is done by the sync. So it runs. So I'm running this for 3 tags. So it'll spawn 3 internal tasks, and then once those tasks are spawned, it'll wait for all those 3 to finish, right? And this, you see, for 1 tag, it took me about 28 seconds. For 3, it takes me 37 seconds. So you get a lot of benefits by doing this async. If you wanted further parallelism, you can, of course, just pmap that. So you take a function that runs async, and then you pmap that function across a distributed cluster. And so you get both sorts of parallelism, both across clusters and parallelism for your data, for your I/O, right? So that's how you build a scraping library in Julia. Thanks for listening. And if I have time for questions, I'll take one.
One question.
Thank you. Thank you.